Hey everyone, I hope you're doing well today. In this video, I'm going to talk about how to find a derivative using the definition. To help you navigate through this video, here are the timestamps. They're also in the description if you want to jump right to them. By definition, I'm referring to this formula here and this formula here. It's important to know that these two formulas or definitions are different versions of the same thing. Notice how the formulas are identical besides the x and the a being swapped out for each other. While the x represents any possible x value on the function, the a represents a specific point that we're talking about. Just keep in mind this a value is going to be our point of tangency. We're going to be trying to draw a straight line that touches our curve at one point. Keep in mind that this a value is really just an x value on the graph, and it's where our tangent line is going to touch the curve. Since the rate of change is constantly changing on a curved line, our goal is to find the slope of the tangent line to the curve at a given point so we know the instantaneous rate of change at that one location. Let's do a quick throwback to Algebra 1 to understand slope or rate of change. Remember, to find slope, we used a formula that said slope equals, or m equals, y2 minus y1, or the change of y, over x2 minus x1, the change of x. While y2 minus y1 told us our vertical change, or our change in y, the x2 minus x1 told us our change in x, or our horizontal change. This ratio of vertical change to horizontal change gave us the slope of our linear equations. Since you've survived so far from Algebra 1 to Calculus, let's see how these formulas are actually related. As we're finding the limit here, we're finding the ratio of the change in the function to our change in x. I just wanted to make this clear so you can see that we're still finding rate of change. Since we're finding an instantaneous rate of change instead of an average rate of change, we need a little bit more of a complicated formula. So what if we want to find the instantaneous rate of change at this location right here? At this location, we know a is equal to -2, or x is equal to -2. At a equals -2, we can see that the tangent line has a negative slope or negative rate of change here. At a equals -1, we can draw another tangent line. At this location, we can see that there's a slightly different rate of change here. It still has a negative rate of change, but it's a little bit less steep. At a equals 0, we can draw another tangent line here, and see the rate of change is 0 at this location. What about when a is +1? You can see here that when a equals +1, the slope of the tangent line is actually positive. And for one more example, when a is equal to +2, we see our tangent line here has an even steeper positive slope. Hopefully that visual gives you a little bit better understanding of what the derivative looks like. Since the rate of change or the slope is changing on each of those tangent lines, we're going to be using the definition of the derivative to find the rate of change at any given point on the curve. In the rest of this video, I'm going to show you how to find the derivative using the definition and how to find the slope of the tangent lines at a few different points. I strongly encourage you to try some of these examples with me so you understand the concepts a little bit more clearly. Let's do some math together now. For the rest of this video, this is the function we're going to be using. If you'd like me to make some other videos with different functions, please comment down below and let me know. First, we'll go through how to find a derivative of this function using the definition. Then we're going to use the definition to find the slope of the tangent line when x equals -1 or a equals -1, since x and a are the same thing. Then I'll go over how to find the slope of the tangent line when x equals 0 or a equals 0. And I'll end the video with finding the slope of the tangent line when x equals +2 or when a equals +2. Let's give it a go. Let's use the definition to find a derivative of this function. F of x is equal to x squared plus 1. You can see the sketch of it to the right. To represent the derivative, we're going to say f prime of x, and that's going to be equal to the limit as h is approaching 0. And instead of f of x, we're going to have to find f of x plus h. That means that every time we see x in our f of x, we have to swap it out for x plus h. From this, we're going to write the quantity of x plus h squared plus 1. Notice how while we used to have an x here, we substituted x plus h instead. The f of x plus h in our definition is represented right here. And now we're going to subtract f of x. Remember that f of x is just our original function of x squared plus 1. So substituting in, we're going to say minus the quantity of x squared plus 1. This is our f of x. And this whole thing up here is going to be divided by h. Now that we've correctly substituted our function into the definition, let's clean it up a bit. First, I'm going to expand this x plus h squared into x plus h times x plus h and add 1 after. Distributing or foiling here, we're going to have x times x, and that's going to be x squared. Then we have x times h, which is going to be xh. Next we have h times x, which is going to be another xh. And finally we have h times h, which is going to be h squared. By combining these two like terms in the middle, we're going to have x squared plus 2xh plus h squared plus 1. We just expanded this first part of the definition so that we can combine like terms or cancel out terms with the second part. Substituting in here, we have the limit as h is approaching 0 of x squared plus 2xh plus h squared plus 1. Again, this came from right over here. And we're going to subtract f of x, which is going to be minus x squared minus 1. This part of the numerator came from distributing this negative 1 to both of these terms here. And this whole thing is still going to be over h. Now it's time to combine like terms and simplify this a bit. Here we can see that this positive x squared and negative x squared are going to cancel out, and this positive 1 and negative 1 are also going to cancel out. Let's write this cleaned up version a bit. So we have the limit as h is approaching 0, and we're going to have 2xh plus h squared all over h. In the numerator, notice how both terms have an h, so we're going to factor that out as our GCF and have h times a quantity of 2x plus h. This is going to be all over h. Since the numerator and denominator have a common factor, we can simplify it by h. Here we can see our limit is going to be 2x plus h. At this point, we can now substitute 0 in for h, so we have 2x plus 0, which means our final derivative here is just going to be 2x. This 2x represents the derivative of our function f of x is equal to x squared plus 1. 2x is going to represent the slope of each tangent line. As the different x values change, the slope of the tangent line at each of these points is also going to change. Now we're going to look at some specific x values to see how the slope of the tangent lines are going to change. Let's use the definition to find the slope of the tangent line when x is equal to negative 1. Since we're talking about a specific value, we're going to be calling this a. A is going to equal negative 1. We're going to be substituting negative 1 every time we see a in the definition. Substituting in here, we're going to have f of negative 1 plus h minus f of negative 1. All of this is going to be over h. Well, we know that f of x is equal to x squared plus 1. Now we have to find f of negative 1 plus h. We're just going to substitute x with negative 1 plus h. Let's substitute x with negative 1 plus h. Here we're going to have the quantity of negative 1 plus h squared plus 1. Now let's subtract f of negative 1. Substituting negative 1 in for x, we're going to get minus the quantity of negative 1 squared plus 1. This whole thing is going to be over h. Somewhere on the side of your paper here, you should expand this so that we can simplify. We have negative 1 plus h times negative 1 plus h plus 1. Distributing here, we have negative 1 times negative 1, which is positive 1. Negative 1 times h is going to be negative h, and h times negative 1 is going to be a negative h, and h times h is going to be h squared. And we still have a plus 1 here. Rewritten, we have h squared, and this negative h and negative h are going to make negative 2h, and this positive 1 and positive 1 here are going to make positive 2. Here's our simplified version of this first part. Let's write our simplified version into our limit and see if we can simplify anything else here. Inside these brackets, we have negative 1 squared, which is just 1, and 1 plus 1 is just going to be 2. I'm going to write this as a 2 here. So we've cleaned it up a little bit more, and this whole thing is over h. Notice this positive 2 and negative 2 can cancel out. So we're left with h squared minus 2h over h. Factoring out an h in our numerator, we're going to have h times a quantity of h minus 2 all over h, and our common factors of h are going to cancel out. Simplified here, we have the limit as h is approaching 0 of h minus 2. As h approaches 0 and we substitute in 0 for h, we're going to get a final answer here of negative 2. This negative 2 represents the slope of the tangent line when x is equal to negative 1. Let's zoom in on our graph here. At this location here, we can see that x, or a in this problem, was negative 1. We also found out that our derivative, or our slope of our tangent line, is going to be negative 2. To draw our tangent line at this x value of -1, we're going to go down 2 and to the right 1 to represent our derivative or our slope of -2. We can also go to the left 1 and up 2 as well. This line right here is our tangent line and represents our instantaneous rate of change when x equals -1. In this example, let's find the slope of the tangent line or the derivative when x is equal to 0. So here we have the limit as h is approaching 0. And we're going to have f of 0 plus h minus f of 0. This whole thing is going to be over h. Now let's substitute our 0 plus h in for x. Substituting in, we're going to get the quantity of 0 plus h squared plus 1. Now let's subtract f of 0. F of 0 is going to be 0 squared plus 1. This whole thing is going to be all over h. Simplifying the first part of the numerator, 0 plus h is just going to be h squared, and we have a plus 1. Simplifying the second part, we have 0 squared, which is 0, and 0 plus 1 is just going to be 1. Substituting these simplified expressions in, we're going to have h squared plus 1 minus 1 all over h. This positive 1 and negative 1 are going to cancel each other out, so we have h squared over h. Simplifying just a little bit more, h squared over h just becomes h. The limit as h approaches 0 of h is just going to be 0. 0 represents the slope of the tangent line at x equals 0. Let's see how that looks on our graph here. At this point on the curve, x is equal to 0. Since we found out that our slope was 0, we know that's going to represent a horizontal line. This horizontal line is our tangent line. When x is 0, the slope of the tangent line is also 0. In this instance, it makes sense it's neither rising nor falling because we're at the lowest point of our parabola. For this last example, we're going to find the slope of the tangent line at x equals 2. When we say x is equal to 2, that's going to be our a value here. Substituting 2 in for a, we're going to get f of 2 plus h minus f of 2. This is going to be all over h. Now let's find f of 2 plus h. F of 2 plus h is going to be the quantity of 2 plus h squared plus 1. And subtracting f of 2, we're going to get 2 squared plus 1. And let's write all of this over h. Simplifying this part, we have the quantity of 2 plus h times 2 plus h plus 1. 2 times 2 is going to be 4. 2 times h is going to be 2h. h times 2 is going to be another 2h. And h times h is going to be h squared. And we have a plus 1. We can see we have some like terms with this 2h and 2h, and we have the like terms here of positive 1 and positive 4. Reordering this and combining, we have h squared plus 4h plus 5. This is our simplified version of that part of our limit. Simplifying the second part, we have 2 squared, which is going to be 4 plus 1, and that simplifies just down to 5. Let's write our cleaned up limit here. We're going to have h squared plus 4h plus 5 minus 5. All over h. Again, these were the simplified versions of the line above. Looking to simplify more, this positive 5 and negative 5 will cancel out. This leaves us with h squared plus 4h over h. Factoring out h, we have h times the quantity of h plus 4 over h, and these two h's are going to cancel out. After simplifying the h's, we have the limit as h approaches 0 of h plus 4. Since h is going to 0, our answer here is just going to be 4. This 4 represents the slope of the tangent line at x equals 2. Let's zoom in and take a look at this on our graph. At this location, x is equal to 2. Since we found out our slope was 4, we can start on this point here and go up 4 and to the right 1, or we can go down 4 and to the left 1. By connecting these points, we form the tangent line at x equals 2. Since our answer was 4, the instantaneous rate of change, or the slope of the tangent line, is 4 at this location. So what have we found in this video? First, we found that the derivative of this function was just equal to 2x. When x was equal to -1, we found out the slope of our tangent line was going to be -2. You can see that on our graph over here. When x equals 0, we found out the slope of our tangent line would be 0. And that tangent line is drawn over here. And finally, when x was equal to 2, we used the definition to find that the slope of the tangent line would be 4. And here's that tangent line here. We had a slope of -2, a slope of 0, and a slope of +4. While there are faster ways of finding these values, this video is dedicated to using the definition of the derivative to solve them. If you found this video useful, please let me know in the comments below or by liking this video. Keep up the good work, and I'll see you in the next one.